Okay, I was looking at how you can model pipe flow in openfoam. So I found a tutorial or a demo case where they set up a pipe, and I've adjusted the mesh a little bit. So you don't need to model the whole pipe, you can just model a section of it. So here it's just a quarter. I mean, you can have as many cells going around the circumference as you want, but I've just kept it fairly coarse. And then I specified a low velocity. So this is the inlet, and it takes a few cells for the flow to adjust. But so what you get is you've got the outer wall where the velocity is 0, and then towards the centre of the pipe you've got the peak velocity. So I think in this case I specified an inlet velocity of 0.01 meters a second. It could be quite different to that, but I don't know, I've just guessed it. And this dimensions of this I've estimated as the diameter of 1 millimeter. So the length of this is only 2 millimeters. So I've just done a really small section of pipe as if it was some sort of needle. And then the interesting bit is that I found a paper which describes hydrogels in terms of their viscosity is in terms of the power law. So the power law just means you're specifying two coefficients to get the viscosity. So visually, the viscosity is related to the strain rate, and it's given here as the shear rate. So across a range of values, 3 different hydrogels, you can see how the viscosity varies. So you can specify a max viscosity, a minimum viscosity, and we know what those K and N parameters are. So the power law model that you specify in openfoam is basically the same thing. So viscosity is in terms of the strain rate multiplied by K to the power of n minus 1. So in order to specify the viscosity for a hydrogel in theory, you could just specify these values K, N, and then the max and min values. That's kind of like limiters for it. So what that looks like in the code is constant momentum. The previous demonstration case had this cross power law, whatever that is. I'm not familiar with that. But for a basic power law model, in the code you just specify the max and min values and then a K and N value. So I'll put in the other values for the other hydrogels, but I've just selected one of them. And then run it. And when you run it, it runs really quick, like in a few seconds. When you run it, it gives you the strain rate of viscosity multiple nu. Well, it tells you the viscosity. So in this case, the peak viscosity is towards the center, and then the viscosity is less towards the outside. So it'll look different for different power laws or different hydrogels, but in this case we've got that. And then you run this other function. To get the shear stress, you have to post-process it to get the shear stress out. And then when you read that in to openfoam, you get the shear stress here. So that's a shear stress. So you can see it's quite large towards the wall there, I should expect. And then if you're interested in the strain rate, that I've done that post-processing using Python calculator, and in the Python calculator I've put in strain mag strain velocity. So that's the strain function that's already in the Python calculator of the velocity. So I think that's the magnitude of the total strain rather than shear strain, if that is even a thing. But this, what we're looking at here, is the overall magnitude of the strain rate based on the velocity gradient. So after running the solution, we've got the velocity profile, we've got the viscosity that is variable across the pipe, and then we've got a strain rate that is that one. We've got a strain that is causing the viscosity to vary, and we've also got the shear stress, which we can we've got the shear stress. So we've got a stress and we've got a strain and we've got the viscosity. So there's quite a few things that you can look at there. And then in theory you could look at the different hydrogels and then put in different values for different hydrogels, then rerun it and do it like that to sort of compare which one is best. But I think once you get a handle on what this plot actually means, then that'll probably give us a better idea about which hydrogel is best for a specific application. But yeah, that's where I've got to so far. So just using a very simple demonstration exercise and putting in the power law for the viscosity and then running it to get the solution, and then that tells us what are the shear stresses in the fluid.